The basic example in this course is a particular example that we're going to have a look at and then return to over and over again throughout the course. Every time we see a new idea, we'll come back and see what this means in terms of the basic example. The basic example is a manufacturing problem, and in this particular problem, we've got a machine shop, and it's producing two products, and they each require time on three different machines. So to produce each product, that product has to spend some time being worked on each of the three machines. And associated to each product, there's a particular profit, and the information is listed in this table here. So here on the left we have the three different machine types, and here in these two columns we have product 1 and product 2. So for product 1, to produce product 1, for each item of product 1, it's got to spend 2 hours on machine 1, 1 hour on machine 2, and 1 hour on machine 3. And each item of product 1 delivers $40 profit. For product 2, it has to spend, for each item, 1 hour on machine 1, 1 hour on machine 2, and 3 hours on machine 3. And 1 unit of product 2 delivers $60 profit. Now for these numbers over here, these represent constraints on the production process, and the constraints in this particular problem are to do with how many hours the machines are available for. So we're told here that machine 1 is only available for 70 hours a week. Machine 2 is only available for 40 hours a week, and machine 3 is available for 90 hours a week. So we've got a lot of numbers here, and the problem is, well, it's a profit type problem. The problem is to maximize the profit. So the question is how to arrange our production schedule so as to maximize the profit. So we want to find the weekly output of each product that's will deliver the maximum product. So this is a typical linear programming problem. This is an example of what's called a manufacturing problem. And the first step is to turn this word problem into a system of equations and inequalities. This is the mathematical formulation of the problem. And the key thing to do is introduce variables. So we're going to let x1 and x2 represent the number of units of products 1 and 2, respectively, produced each week. Now notice here, the definition of the variables is explicit and clear. You can't just say let x1 equal product 1 and let x2 equal product 2, because that's just not clear. x1 and x2 are the number of units of products 1 and 2 produced each week. That's clear. If in your answer to a homework problem or an exam problem, you don't say clearly what the variables are, you'll be punished heavily, because mathematical communication and communication in general is a key part of this course. You've got to say exactly what your variables are. That's a critical part of this step. The other variable we'll need is the weekly profit, Z, be measured in dollars. So Z in this case is 40x1 plus 60x2. The reason for that is you get $40 profit for each item of product 1 and $60 profit for each item of product 2. So that's our our profit function, Z, and our problem is to maximize Z, but we've got constraints. And the constraints concern the amount of available time that we have on the different machines. Machine 1 has a total number of hours available of 70 per week. So we can't spend more than 70 hours per week working on machine 1. Now, item 1, for for product 1, for each item, we need 2 hours on machine 1. For product 2, for each item, we need 1 hour on machine 1. So if we have X1 units of product 1 being produced per week and X2 units of product 2 being produced each week, then the total amount of time this will require machine 1 is 2x1 plus x2. So this number here cannot exceed 70. Must be less than or equal to 70. And if you look at the constraints on machine 2 and 3, you get similar inequalities. So the constraints on the time availability of the machine gives us 3 inequalities, and we're trying to maximize this profit function subject to these inequalities. Well, there are more inequalities, but they're just like trivial ones, and that is you can't spend a negative amount of time on a machine. So x1 and x2 should both be non-negative. So this is our mathematical formulation. Maximize z subject to these inequalities. This is called the feasible region. This is the feasible region. It's the set of points that satisfy all the constraints. So our job is to find the point in the feasible region which gives us the maximal value of z. The z here, the profit function, 40x1 plus 60x2. It's just this function here. So the idea is to draw some of the level sets for this function z. So if you just pick z to be a specific value and draw the corresponding line, you'll get one of these dotted lines. As z varies, you get lines that are all parallel to each other. So for instance, this one here going through the origin, that's the equation 0 equals 40x1 plus 60x2. The one that goes through here, for instance, that's going through the point where x1 is equal to 60 and x2 is equal to 0. So that must be the equation corresponding to z equal to 60 times 40, which is 2,400. So in the practice class, you'll get to learn how to draw feasible regions like this. And the idea, and to draw the level sets of z. And the idea is that you imagine the level sets of z sweeping across the feasible region. So this point here is on the line. The origin here is on the line corresponding to z equals 0. This one way up here is the line z equals 2,400. And then, but this line, you see, doesn't intersect the feasible region. What we want is the point on the feasible region which has the biggest z value. So as you can see, as the dotted lines sweep across the feasible region, this corner here will be the point which has the highest z value. And that's the point that's got coordinates 15, 25. 15 and 25. And its z value is 2,100. So that 2,100 is the biggest z value that you can find for any point in the feasible region. And that's the solution. So you can, this is the graphical solution. The idea is you just draw the feasible region, you draw some of the level sets, you imagine the level sets sweeping across the region, and you look for the last point, the very last point where one of the level sets touches the feasible region. That'll be your biggest value. So just finally some terminology. For our the function we're trying to optimize here, this is called the objective function or the profit function. Its coefficients are called the cost coefficients. For our constraints, the the variable are the decision variables, and the numbers that appear next to them are the constraint coefficients. The numbers on the right hand side are called the resource values. And our answer, the x1 and x2 values, they're our optimal solution, and that gives us an optimal value for z. The x1 and x2, as I've just said, are called the decision variables. Any point that's in the feasible region is called a feasible solution, and the optimal solution is the very special feasible solution, which gives you the best possible z value. Okay.